Hello, students. I hope you all are well and doing great and enjoying the power of the online teaching. So today I have come up with new topic: force between two parallel currents and the ampere. This is NCRT chapter number 4, magnetic effects of current and magnetism. So let us enjoy the lesson. Get ready with notebook and pen and note down the important things. So look at the following figure. This is the figure. Now see, these are long straight conductors. Current through them is IA and IB, separated by small d distance. This conductor B is placed in magnetic field produced by A. Similarly, conductor A is placed in magnetic field produced by B. So let us first understand this case. This current carrying conductor is placed in magnetic field BA. This field is produced by the conductor A. And direction according to the right hand thumb rule. Set your thumb in the direction of current. So turn of the fingers will tell you the direction of magnetic field. So when we hold this conductor A in such way that thumb points in this direction, so this is obvious. On this side of this conductor, magnetic field will be downward, perpendicularly downward, and on this side this will be upward. So now this conductor B is placed in magnetic field BA. This field is produced by conductor A. Its direction is perpendicularly downward. So now what is the situation? To find the direction of force, we apply left hand thumb rule. Settle this finger in the direction of field and settle this finger in the direction of current. Thumb is indicating that force is inward. Force is towards the conductor A, FBA. So I have applied right hand thumb rule to find the direction of the magnetic field, and Fleming's left hand rule is applied to find the direction of force. So let us apply Ampere's circuital law, and you already know the field produced by any straight conductor, long straight conductor at distance d is mu naught Ia divided by 2 pi d in this case. As such, formula is mu naught I divided by 2 pi r. So here distance is d. Distance of this point from conductor A is d, and current in this conductor is Ia. So this is the magnitude of the BA. Now this conductor is carrying current IB. So force on this conductor. So force on this conductor will be F is equal to I L B sin phi, and here phi is 90 degree. So force is ILB, that is I length of the segment of the conductor and capital B the magnetic field. So we apply this formula. So FBA, force on B by A, is equal to current IB, length of the segment is L, capital L, and field is BA. So this much is the force applied by this straight conductor, very long conductor having very negligible cross sectional area. Now put the values of BA here. When we put the values of BA, force on B by A, force on B by A is mu naught IA IB divided by 2 pi d into L. And direction is towards the A. FBA is towards the A by FLH according to rule FLH, Fleming's left hand rule. Now, again, let us think over force on A by B. Now B is producing the magnetic field and conductor A is placed in the magnetic field produced by B. So if we apply right hand thumb rule and hold this conductor B, this thumb indicates the direction of current. Obviously, you will get that on this side of the conductor B, direction of field is upward, upward, opposite to BA. So when direction of magnetic field is reversed, but direction of current is not reversed, force direction will also be reversed. So FBA was from B towards A. Now what will be the direction of FAB? FAB, A to B. Apply again this FLH, Fleming's left hand rule. Settle this in the direction. Settle this in the direction. So thumb indicates the direction of FAB. This is towards B. And magnitude will be same. Similarly, you can find this FAB. Force on A by B. Same magnitude. And direction, I have already explained you. So now this is very clear. FAB and FBA both are equal in magnitude but opposite in direction. So therefore, here Newton's third law of motion is applicable. For every action, there is equal and opposite reaction, and action and reaction never act on the same object. Therefore, vector FBA plus vector FAB is equal to 0. Or you can say vector FBA is equal to minus vector FAB. Magnitude wise same, direction wise opposite. Now one more important conclusion is here. See, direction of current is same. Currents are parallel, but force is attractive. So if direction is anti-parallel, force will be repulsive. And here charges are moving, but when charges were at rest, like charges repel each other and unlike charges attract. So here this is opposite. For the memory purpose, this is very important. That here situation is opposite. Parallel currents attract, anti-parallel repel. Just I am telling, keep in memory. Sometimes we confuse, no, what will be the force. So this thing will help you in memorizing the direction. So now we know FBA is the capital FBA is the force on B by A. Small FBA is force per unit length. That is FBA by capital L. And from this we get FBA by L is mu naught Ia Ib by 2 pi d. Divided by L you will get force per unit length. This is force per unit. And direction of this FBA or FAB, I am repeating again and again, by applying Fleming's left hand rule we can obtain the direction. Now what is the utility of this small FBA? We can find the definition of 1 ampere. And you know ampere is one of the 7 SI basic units, fundamental units. Let us derive the definition of 1 ampere. We already know this FBA is equal to mu naught IAB divided 2 pi d. Now see this figure. In this figure we will put some conditions. Okay. So see, I have multiplied numerator and denominator by 2. So this will become 4 pi. Mu, I have separated mu naught by 4 pi because its value is 10 raised to power minus 7. Now this portion is 2 IAIB divided by D. Again I have clubbed 2 into 10 raised to power minus 7 and separated IAIB by D. Now here I put condition that both the conductors, straight conductors, long straight conductors having equal current, that is I. So IA into IB will become I square divided by T. Further few more conditions. Suppose force between these two straight conductors is 2 into 10 raised to power minus 7 Newton. Now what is the situation? They are having same magnitude of current. Force is 2 into 10 raised to power minus 7 Newton. This force is per unit length. Distance is 1 meter. This force is per unit length of wire. This 1 meter is distance between the wire. So don't confuse between these two things. Okay. This is force per unit length and this is the distance between the wires. 1 unit, 1 meter. So now put conditions. These conditions in this formula we get I square is equal to 1. Because when we substitute, this bracket will be cancelled. D is already 1, you will get I square is equal to 1. And by taking square root, 1 ampere. I have neglected here plus minus sign. And you already know what is the meaning of plus minus sign, that forces may be attractive or repulsive. Or direction of current can be same or can be opposite. This we can conclude from plus minus. But here I am discussing the magnitude. So let us define the 1 ampere. We can define in our own language also, in our own style. What is the situation? If two long straight conductors are placed at 1 meter distance and same amount of current is passing through, same magnitude of current passing through, and they experience 2 into 10 is to power minus 7 Newton force per meter of their length, then current passing through these wires is definitely 1 unit, that is 1 ampere. This is what written in this statement also. So here I would like to remind one thing. In exam, in haste or some stress, students forget to write Newton per meter word. They just write Newtons. Per meter word, skip. This is the common mistake. Even intelligent students also commit this mistake during the examination. So take care while defining in the examination. Now, this definition was adopted in 1946, but still, this is theoretical definition, not completely fit, because here we have neglected the impact of Earth's magnetic field on force, and also such a long straight conductor is practically very difficult. To make very long straight conductor, we have to convert conductor to in some sort of coil having multi turns. That will also affect the formula. So here this definition is theoretical, not practically. Better practically we adopt the definition that 1 ampere current is the when 1 coulomb charge flow in 1 second through any cross section of the wire or conductor. So this is all about this very small lesson plan. I hope you have enjoyed it. Keep watching my videos, post your comments. Thank you very much. Stay safe, stay healthy. Bye bye.